All right. Okay, so our topic was transform coding, and for that we were beginning with the concept of what is a transform and how do we make it and why do we make it. These are two fundamental questions, but before that, another fundamental question was what is really the transform? What makes the transform? And it's nothing more than a change of representation or a change of basis for the representation of the same signal. So we're not really changing the signal in transforms. The signal is there. We are altering our perspective, the way we look at the signal. And that makes the transform. It's like in the Euclidean geometry, it's like changing the basis axis, rotation of the axis for the representation in two-dimensional Euclidean framework, let's say. We rotate our basis vectors from 1, 0, and 0, 1 to a rotated version of it. And a vector, a point on the two-dimensional space, stays at the same place, but its new representation is a different representation. So from one representation to another representation, that would define a transformation. That's what we had. And for orthonormal basis, it's easy because in an orthonormal representation, let me repeat that very quickly. In an orthonormal representation of, let's say, why is it blue? Let's switch it to black. If x of n in discrete time, it's easier to mention about that. If we have this kind of a representation, k from minus infinity to infinity, the range of k may vary, it may be finite, of ak, and here we have phi sub k of n. So these phi sub k of n's are our new basis vectors for the representation of x of n, where if they are equal to, if phi sub k of n are equal to delta n minus k, like here, then the representation is quite simply, where do we have it? Yeah, it becomes like this. X of n is equal to something like this, where a sub k will be easy to evaluate, to find. They will become x of k. And that's a convolution sum, as we know of. Here is the thing. And you may believe it or not, but this is also a transformation, but it's an identity transform. We didn't really change the original basis to represent x of n. If you say x of n, you already talk about delta n minus k basis, and the values of x of n at n is equal to k are the coefficients. So the coefficients already represent x of n. But the way to obtain those things, including in this particular example, is very simple, as long as these phi sub k of n basis signals are orthonormal. So if these are orthonormal bases, by the way, last week we talked about orthogonality of two things using inner products. And in order to be a basis, it must span the space. So space spanning property must also be there. But let's assume that they are all available to us. If these are orthonormal bases, then AK from here can be easily found to be the inner product of x of n and phi sub k of n. This is how we find it. You may make an analogy with linear algebra. In vector matrix notation, it's the same thing. This inner product is the thing that gives you these coefficients, AKs. But making an inner product for signals, well, it's also quite similar to the linear algebra concepts. It's like term by term multiplying the elements consider a vector and another vector. What's the inner product of two vectors? It corresponds to the summation of term by term multiplication. So you term by term multiply and then sum them up. So this inner product is essentially term by term multiplication of x of k. X of k is it's a bad choice. Let me say x of n still, but then no. Well, okay, it will be x of n. And phi k of n, and then summing up over all n, like this. So this is the inner product, except a detail here, which is also valid for linear algebra, but we never use it because we usually use real valued linear algebra. But for complex valued signals or vectors, essentially you need to put a conjugation for the second term in this inner product. So this is our overall framework. And this automatically defines a transformation from the values of x of n, like x of 1, x of 2, x of 3, etc., to a sub k, which is a sub 0, a sub 1, a sub 2, etc. So from x to a things, this defines a transformation. A transformation of interest is the Fourier transform, actually, where so this is essentially an example, but it's a very general example, so you can think of it as a whole chapter. Phi sub k of t, I'm gonna call it in normal parentheses and t. As you see, although my example was in discrete time, this signal could also be a continuous time variation. It could be multiple dimensional too. We will come to that. But it could be continuous time as well, where this summation converts to an integration. Again, in this inner product, again, this summation converts to an integration. That's a possibility. That's also available for us to make interpretations or to make transformations in continuous time signals. This example is therefore a continuous time case. This one is equal to e to the minus j 2 pi k t over t0. Notice that it is parameterized both in terms of this index of k here, and instead of n, now we have t, which is also available here. So this expression is phi of k and t. You can also write it like that, if you wish. It's phi of k and t, or k and n. One of them becoming subscript is not a critical thing, but it helps us to make an observation that it's actually, this one, for example, is essentially a function of n, and it is indexed by k. So there are different functions of n's. This is also the same. It's a function of t, and there are different functions of t. There are different time functions by altering this k. That's what we obtain. And the result that we get from this kind of a representation requires that this thing needs to be orthonormal, which means it's orthogonal to other phi k of t's, and its norm, you have to define a norm, you have to define a distance for these operations. According to the signal norm, it must have a unit norm. Norm must be equal to 1. Whereas for this one, it's not. It's actually, its norm is t0. Because it depends on t0. By the way, the norm that we will be talking about will be something like this. So the norm of this, let me put it in square terms. After that, you may take the square root of it. Will give you the integral of this 2 pi kt over t0 and its conjugate times its conjugate. which makes e to the j 2 pi kt over t0 dt. And since this is a periodic signal, for periodic signals in harmonic theory, you have to define the inner product within the period. So this integral must be taken from 0 to capital T0, which is one period of that. So when you take this integral, you notice that this thing cancels with this one totally. It becomes 1, in other words, e to the 0 it makes. And e to the 0 is 1. So 1 times dt, 1 times dt's integral, or 1's integral, is t itself. And from 0 to t0, that makes t0. So the square norm is essentially t0, and the norm is therefore the square root of t0. So from here, we should normally apply not this phi k, but a new red phi k of t, which is like 1 over square root of t0 e to the minus j 2 pi kt over t0. But we're not going to do that. We're still going to use the black one because of historic reasons, because it will correspond to Fourier series. And in the Fourier series, we don't really make it unit norm, essentially. It is orthogonal, by the way, but it's not unit norm. So in the inverse transformation, we will compensate for the non-unit norm case by multiplying with 1 over t0. So the forward transformation or the inverse transformation, in one of them, we are going to use 1 over t0, so that we don't use 1 over square root of t0 in both sides of the forward and the inverse transformation. So the inverse transform, which is the representation of the signal, is like this. It's x of t is equal to, for all n, an, for all possible n, of course. So what are those possible n's? We may want to discuss about that. E to the minus j 2 pi kt over t0. So let's say that this is the representation. By the way, it gives you essentially the inverse Fourier series or inverse Fourier transform representation, where the Fourier series are essentially a n. So I used n. Why am I using n? Let me make them k. Sorry about this. Let's say a k's like this. It makes more sense. And the way to discover the Fourier series coefficients, we know the name by coincidence, the AKs, which is the transform, the Fourier transform, as we already know. What we have to do is we have to take the inner product of x of t and phi k of t, but within a normalization factor. So actually I have to use a 1 over t0 times phi k of t, because I didn't choose phi k of t to be unit norm, which makes the integral, by the way, the integration is again within one period from 0 to t0, or within a duration of t0, whatever that duration may be. Its length must be t0. X of t times 1 over t0 times e to the minus j 2 pi kt over t0 conjugate dt, right? This was our inner product, which makes 1 over t0 integral over t0 xt e to the plus j 2 pi kt over t0 dt. This is ak. So you may remember from signals and systems already that this is the Fourier series coefficient evaluation formula, or the Fourier transform for discrete time, for continuous time and periodic signals. We have other systems as well. So this and this, which is this and this, makes a transformation pair, an inverse transform and a forward transform pair. But those pairs could be obtained by just knowing that we have a basis signal in this form, or more generally in this form, and I just applied it and I obtained the forward and inverse transformation. Let us look at the others in the form of a list. I'm not going into the details of how to construct them, but I want to give them as further examples, like the continuous time Fourier transform, which is actually the first Fourier transform we usually learn. The first Fourier transform we usually learn was the continuous time Fourier series. So after the series comes the Fourier transform. So how did it look like from our perspective? It essentially looks like this. X of t has this representation, an integral, and alpha of f, we can write in a parentheses, and actually this alpha of f is capital X of f, by the way, in the Fourier transform. It may be in the form of an omega parameter or an f parameter. It depends on how you define the Fourier transform, within the frequency in hertz or within the frequency in radians per second concepts. But this one is just using the hertz. So alpha of f times e to the j 2 pi f t df. So here what we have is the basis signal, which is equal to e to the j 2 pi f times t. So it is phi sub f of t. You can think of it like that. And the integration is an infinite integration from minus infinity to plus infinity. So it's the most general way of putting things. So from there, how do we define alpha of f, which is the Fourier transform, like the capital X of f? It is the inner product of x of t and this, if this is unit norm, if this is orthonormal. It is again orthogonal, but not unit norm, again, unfortunately. And because of the historic reasons, somehow people just prefer not using the normalized things. And for this case, the norm, the square norm of this one is actually 2 pi. So I have to divide by 2 pi in the opposite operation, just like dividing by t0 here. So the answer to the inverse operation is within a scale of 1 over 2 pi, the inner product of x of t and the conjugate of the previous bases, which is e to the minus j 2 pi ft dt. And we already know that these two equations are clearly the Fourier transform and inverse Fourier transform definitions. The Fourier transform is the second one. The first one is the representation of the time signal, which corresponds to the inverse Fourier transform. And then the continuous time Fourier series was already given. Let's continue with another example, which is the discrete time Fourier series, where x of n is given as 1 over capital N. This time the normalization is used in the representation. I don't know why. The summation within one period. This capital N is the period of the discrete time signal, because we know that the discrete time Fourier series are applied to discrete time periodic signals. So capital N is the period here. Alpha k, which are the Fourier series coefficients in discrete time, e to the j 2 pi n k over capital N. So k is like the Fourier series coefficient index, and n is the time index. So how do we find alpha k, the Fourier series coefficients then? Now we have to take the reciprocal of, or we don't need to use the 1 over n or whatever, because it's already used in the inverse transformation in the first line. So this is simply a summation, immediate summation. It's not k, this is wrong. It's n from 0 to n minus 1, which is one period. Again, x of n times the conjugate of the bases, which is e to the minus j 2 pi n k over capital N. So these two are the forward and inverse discrete time Fourier series, which are also known as the discrete Fourier transform, DFT. So DFT, whose fast implementation, as we all know, is FFT, the fast Fourier transform, is not the discrete time Fourier transform. The discrete time Fourier transform gives you continuous frequency. The one that gives you discrete frequency, the sampled version of that, is essentially the discrete time Fourier series. And the last example is the discrete time Fourier transform. Here, discrete time Fourier transform, which has the representation x of n to be equal to, again, because of the normalization issues, we have a 1 over 2 pi, because the basis, again, is not a unit norm. And the range, or actually the domain of the Fourier transform, or the transform parameter that we have, which is capital X of omega, is 2 pi periodic, as we all know, because the discrete time Fourier transform provides us with a 2 pi periodic Fourier transform. So this this integral is either from minus pi to pi or from 0 to 2 pi with a duration of 2 pi, actually. Let's say from minus pi to pi as one example. Alpha of omega, I put it in the subscript, but it doesn't need to be. It could be well inside the parentheses, which is essentially the Fourier transform. E to the j omega n d omega. So this kind of a representation of a discrete time signal is available to us, and it's in the form of an integration. It's interesting. So the transform, the signal can be discrete, but its transform can be continuous. The signal can be continuous, but its transform can be discrete, which is the discrete time Fourier series, by the way. Or both of them can be continuous, or both of them can be discrete. So all these four combinations are possible to us. And all you need to do is you have to properly define your inner product. By the way, alpha omega, which is actually the Fourier transform, is the inner product of x of n, which requires a summation. And here, n is from minus infinity to infinity because it's normal, arbitrary discrete time signal. E to the the conjugate of e to the j omega n is e to the minus j omega n. And that's it. Because it's a summation, we don't have dn or anything. So these four examples, I have given 3 examples here. And the first example was already for the discrete, it's continuous time Fourier series. Okay, this one already. So it makes 4 examples, and these are very typical examples of alteration of basis to construct the transformation. But for our case, these are just examples, and we will have to continue with a more generic way of looking at mostly discrete time signals, because we will be doing compression. So for compression side, continuous time transformations are hardly used because we don't have the continuous time signals. We sample them in computers. So we are going to do compression in computers. Therefore, we will assume that the signals are discrete time. And their transformations are also in discrete time because we don't know how to handle continuous time functions in computers. So, but these concepts are necessary to know. The continuous time versions also exist. So I will give an end to these examples, and I will continue with finite length discrete time signals, which are the signals that we want to compress. They are of our interest because this is a compression course that we are seeing. So the things that we will be concerned about is the representation of f of n, which is the discrete time signal, using a new basis, but it's going to be finite. Because if it is finite, you will see that it's possible to make this representation like a vector matrix multiplication. And in two sampled cases, two-dimensional cases, it will be easy to draw them on the graphs. So this is f of k, which is the new coefficients. Previously, I was writing it like a sub k, but since we know the Fourier transform is usually converting the lowercase f to uppercase f, from that kind of a notation, let's use an uppercase value of the same letter. Let's call that, after the transformation, it becomes capital F of k. And here I will have h of n and k, which is actually h sub n of k, you can think of it. Yeah, it's actually incorrect. I'm sorry. Let me switch their places. H sub k of n, because it's a function of n, and I'm combining those basis functions of n's with some scales, and the combination of these h of n's with different h of n's will give you an f of n with these new scales. But you can also write it like this because it is parameterized in two ways now. It's parameterized both in terms of n and k, or k and n, whichever you may choose. So this is my representation, and here this thing is called the inverse transform kernel. That's a name given to it, but it's essentially the new basis signals that I'm using, which corresponds to the inverse transform kernel. And we know that if they are orthonormal, if these inverse transform kernels are orthogonal to one another for different k's, for different n's, then it becomes a basis, provided that they are unit norm. So if they are orthonormal, let's say, then it makes a basis. And if they are a basis, then capital F of k is obtained as the inner product of f of n and this inverse transform kernel in the inverse transform kernel in the inner product case. So we know that it's f of n inner product with h, n, and k. But I'm going to write it in its own inner product definition sense in a different way, like summation n from 0 to capital N minus 1 f of n And I am going to call this G of K and N, which essentially corresponds to the conjugation of H of N and K in a sense. But this time I'm attacking the problem from a different perspective. Let's assume that whatever this H is, H of N is, let's say that it's not necessarily orthonormal. It's just any function of N and K. And with this representation, is it possible to find another representation of G of K and N such that this time when I make this combination, it gives you capital F of K. It gives you these. Is it possible? First, let's start from that. And what are the fundamental constraints on its existence? Is this kind of a transform and inverse transform available to us? And the answer becomes clear if we can understand what we see here, and we will compare it with the which corresponds to the inverse transform. We will compare the transform and the inverse transform in a different notation. And that different notation is this. This is going to be an F vector. It's a finite F vector. I'm notating with a bar underneath. Is equal to a vector I'm going to call capital H. It's not a vector, it's a matrix actually, which corresponds to this matrix. H, N, and K. I'm making it in the form of a matrix which has two parameters. One of them is N, the other one is K. So it makes a matrix, right? And when I multiply that matrix with this capital F vector, usually I use capital letters for matrices and lowercase letters for vectors, but unfortunately, I'm using this one to be a vector, whereas this one is a matrix, and this one is also a vector. Okay, with this kind of a notation, it's possible to write this inverse transform in the form of this matrix vector multiplication. Indeed, this summation corresponds to a vector matrix multiplication. And the second one, which is here, actually makes capital F vector is equal to G matrix, which is a matrix that is constructed from this one, times, times the F vector. Okay. So this is again the vector, the input vector. This is the matrix, which is like the transform matrix, essentially. This G matrix is called the transform matrix. And the output is a vector, which is the transform of lowercase f. So what is the necessary condition for these two to exist? As you see from the first line, from here, we can say that f is essentially h, capital H inverse times lowercase f. So we can say that G is actually the inverse of H. So whatever H you may have, and say that it's the inverse transform kernel, which may construct or render a matrix, its inverse will be your transformation matrix. So what is the condition of the existence of such a transform? The condition is only so that the matrix inverse must exist. So inverse of H or G similarly must exist. It must be invertible. It's a square matrix, capital N by capital N. They are square matrices. and their ranks must be precisely equal to capital N. If you have that, without thinking of any orthogonality or orthonormality, whatever issues, you can simply, very simply say that if G is the transformation, then the inverse transform is G inverse, G to the minus 1. And it makes many of the things easier to understand in terms of discrete time transformations. But if G and therefore H are orthonormal, that means it's a unitary matrix that we have. And for unitary matrices, we have very nice properties. So if G or H inherit from orthonormal basis, then G or H become unitary matrices. A unitary matrix have a lot of nice properties. Let me give you some of those nice properties of unitary matrices, which correspond to orthonormal transforms. Fourier transform is one of them, except for a scale. So it's not really very normal, but it's orthogonal at least. When they are unitary matrices, they have these nice properties. The first one is, without starting to write the properties, I will say that we will be talking about, for example, V is equal to A times U. So A is our transformation, U is our input vector, and V is its transform. So A is the transformation here. With this kind of a transform, but it's a unitary transform, it's a unitary matrix, this capital A. It makes these nice outcomes. V norm will be equal to the norm of A times U, which is A times U at the right-hand side, and at the left-hand side, it's conjugate transpose, A conjugate transpose U conjugate transpose. So the orders are also flipped, because we know that when you make a transposition, the orders of the multiplication also changes. The square root of it is actually. So let me put it like this: the V magnitude square is equal to A times U magnitude square, which is equal to this. It's easier to make an interpretation in the square norm sense. The square norm is this. And this thing is from this property, A conjugate transpose times A, if A is a unitary matrix, is an identity. Because A inverse is equal to A conjugate, or let me, A conjugate transpose. Let me put it like this: G inverse is equal to G conjugate transpose. That's what it makes. So an identity comes in between here, which has no effect. It simply becomes U conjugate transpose times U, which is automatically the square norm of U by definition. So what did we obtain? We obtained that this square norm of V and the square norm of U are the same if you have the orthonormal transformation, which makes a unitary matrix. This is also known in Fourier theory, and from signal science systems, you may remember this as the Parseval's equation, or the Parseval's theorem. After taking the Fourier transform, the energy of the signal does not change. as the time energy. So these two will remain the same if it's an energy signal. If it's a power signal, of course, you have to define accordingly. So orthonormal transforms are energy preserving transforms. The second one has some further details. I will have to write those details separately for random signals or for random vectors. In our case, let's assume that U is a random vector whose items are random values from a random signal. I will have to define a few things. First of all, the norm I have to define, the square norm. This is a definition, okay? Is the expected value of U conjugate transpose U. So for random signals, we have to use the expectation operator. This is quite similar to what we used for predictive coding. And since we are doing compression or coding, the signals of our concern will always be random signals. We cannot really talk about deterministic signals for compression purposes. If it is deterministic, if it is there, it has no meaning to try to compress it because its representation is there, it's there. So random signals are the important ones. So this is the norm of U, the square norm of U, and the mean is defined to be the expected value. By the way, this is a vector. The mean vector is the expected value of U vector, which gives you a vector. And the covariance of U, we all know these things from predictive coding, is by definition expected value of U minus mu U. So this is not mu zero, but it's actually mu U. Let me write it like this. Times U minus mu U conjugate transpose. This is the covariance matrix. By the way, for the examination, the covariance matrix evaluation for all of the students were almost the same as each one another using for loops, which is not incorrect, but it's a very inefficient way of doing these things using for loops in MATLAB. We have xcov and xcor for cross correlation. So if you do the cross correlation of the signal with itself, it will be autocorrelation or autocovariance. So it was essentially just one word. Instead of those one words, you were just doing a lot of for loop expressions, which is somehow a pity for the examination for you. So let's continue. Now from here, the first observation is regarding what is the mean of V. V is A times U, okay? So what is the mean of V? By definition, it is the expected value of V, of course. And that is equal to expected value of A times U. And A is not a random entity, so it can be taken out of the expectation operator. A times expected value of U is here, which is equal to A times mu U. So mu V is equal to A times mu U, which means the mean vector is also transformed with the same transform matrix. A is the transformation matrix, so its mean is transformed immediately. This is the first observation under item number 2. Second one under this is about the covariance of V, not U, but V. And again, it's by definition the expected value of V minus mu V times V minus mu V conjugate transpose. All right. And that is equal to expected value of V is A times U. Let me write it. A times U. Mu V is also A times mu U. So A times mu U. And the right-hand side is its conjugate transpose. A times U minus A times mu U conjugate transpose. And that is expected value. Now, I can put these things into a parentheses of A, and that parentheses of A can be taken out of the expectation operator from the left-hand side later. But for this time, I will just write it like this: A times U minus mu U. Okay, it's here. And for the right-hand side expression, there is a conjugate transpose, so the multiplication order will be interchanged, and it's going to be into a parentheses like U minus mu U conjugate transpose times A conjugate transpose. I hope you can follow this, why this order is different at the left-hand side and at the right-hand side, because at the right-hand side is the conjugate transposition of that, and because of the transposition, the place of A now become at the right-hand side. Now I will take this A out of the expectation operator from the left-hand side, and this A conjugate transpose out of the expectation operator from the right-hand side, like this. And in between, I will have whatever it is, whatever left. Like this. And now we know that this is the autocovariance of U, Cu in other words. So the whole thing is A times Cu times A conjugate transpose. So the autocovariance of the transform is transformed in a way by multiplying from the left-hand side by A and from the right-hand side by A conjugate transpose. And remember that A conjugate transpose is the inverse of A inverse for orthonormal signals, for orthonormal transforms. So it's like A times this times A inverse in a way. It's not as simple as transforming the mean with the same transformation. It's a little bit more complicated. It's more than that. It's not only transformed, but also transformed from the right-hand side. By the way, if you don't use these mean subtractions, these subtraction terms, then this will become Rx, capital R sub X, which is, or capital R sub V for this case, of course, if the signal is V, which corresponds to autocorrelation, not the autocovariance. If you subtract the mean, you will get the autocovariance. If you don't subtract the means, you will get the autocorrelation, capital R. And the same formula holds for autocorrelation too. Let me write it in a different color, like in blue. R sub V is equal to A times R sub U times A conjugate transpose. This is also valid, of course. It's easier to show it this way. So these are the properties of the unitary transform matrices. Let me check my time. It's already approaching to 10:30. It's 10:23. I think the concepts that we have seen until now are quite a lot. So it will be a wise decision to give a break at this point. I will give a break, and I will, after that, roll back a little bit to the transform expression in terms of linear combination of basis vectors, etc., to 2 dimensions, because 2-dimensional transformations are also very critical for us. It's perhaps the most fundamental thing that we will be compressing in most of the times. Right? We usually compress images or videos which are consisting of frames of images. Therefore, 2-dimensional transformation is also somewhat critical. These are valid for normal 1-dimensional transforms. So what about 2-dimensional transforms? How can we make a notation of those things, which is not a big deal, but the transform kernel and the inverse transform kernel representations will be just longer. And we will not be designing 2-dimensional transforms. The transforms that are designed or constructed historically are usually 1-dimensional transforms, but we apply it to the rows and the columns of an image in 1 dimension to say that, well, that is my 2-dimensional transform. So how can we do that? What's the relation with the 2-dimensional, originally 2-dimensional transformation and pseudo 2 dimensions constructed from 1-dimensional horizontal and vertical processing? We will need to make those observations too, because it's our duty to make compression, and image compression is a fundamental issue for our case. So right now I want to give a pause, give a break until 11 o'clock. And at 11 o'clock, I will continue at the same address. Okay, so let's meet again at 11 o'clock. If you may have some questions, you may think about how to ask those questions after the break too. So see you then.
See you.
See you.